My name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you've chosen to join us today. Let's go inside. The lecture's about to begin.
Welcome to our second distinguished lecture series. Today we're really honored to have Reddy from Carnegie Mellon University professor there. He's known best to you as the director of the Robotics Institute, has been so for a long time, and he's currently dean of the School of Computer Science. And so he has an unreasonable amount of administrative responsibilities these days, but his shoulders can bear it. One of the reasons his shoulders can bear it is due to his background. His background, he comes from a farming community in India. He first became interested in math and science early on when he experienced the joy of discovering proofs in geometry in elementary school. That can turn anyone on. It certainly did for Raj. As he says, he was quickly swept up into the track of math and science and received a civil engineering degree from a private college in Madras. At that point, he decided to leave India and went to Australia as an exchange student under Professor Hall. Professor Hall had just come back from England and was all excited about using this new thing called a computer for structural design. The machine they used, I'm sure you all remember, this is 1958, was an English Electric Deuce Mark II. Remember that machine? Mercury delay lines, cathode ray tube, This is a new design, this rectangular shape. It used to be round on his machine in those first days. In fact, they did then what was an innovative concept. They attached sound to the CPU so you could hear the algorithm. And I remember the same thing. Believe it or not, you could tell what was running. And when it started whistling, you knew it was in a tight loop and you were in deep trouble, for example. Now, how did Raj learn to program? He learned to program by watching Professor Hall one night verbally saying what he was doing to get an application going in a high-level language which did matrix manipulation. The next day, he was required, in fact, to implement an algorithm for matrix manipulation, and he had to generate the algorithm, implement it, get it running. In Australia, he received his master's degree in structural engineering. He then went on to work for IBM World Trade in Australia in the applied sciences. He worked with astronomers and statisticians, and he did systems work in those early days, those early days of computing. After 3.5 years of IBM, he decided not to continue, as any sensible person might who was interested in a PhD. And he decided not to continue with engineering, indeed. So he applied to Carnegie Mellon and Stanford for a PhD program. Carnegie made a drastic mistake of not accepting him. That part of the story will continue in a moment. Stanford did accept him. AI was not his prime target at the time. Rather, his interest was in understanding intelligent behavior. He was not interested in creating an all-knowing, all-knowledgeable automaton, but rather he wanted to develop systems that exhibited intelligent behavior. For example, an intelligent assistant to watch him fumble at his keyboard and explain to him what the proper commands and procedures are. When he arrived at Stanford, he asked to see Professor Forsythe. And the answer was, it would take you 3 months to see him at the earliest. So instead of setting up an appointment, Raj did the smarter thing. He scored second best in Forsythe's class, and Forsythe called him. In addition, when he applied, he had mentioned on his application that he was interested in AI. And so he was assigned to the little-known Professor John McCarthy. That was the fall of 1964. The computer science department was formed in early '65, and he was one of 4 students who passed the entrance exam for acceptance into that program. The others were Bill McKeeman, Bob Beliskov, and Jim Painter. Raj and Bill were the first 2 students to get a PhD in computer science at Stanford. And it's not totally clear which one was first. They argue as to who got out the first hour or the second hour. They were both taking the exam at the same time. That was 1966. They were both hired as assistant professors. Raj did his here work there at Stanford. His department unanimously recommended him for promotion, but the Stanford policy in those days was not to accept any of their own graduates beyond that assistant professor point. Carnegie Mellon jumped at the opportunity to correct a serious mistake from years ago and quickly hired him on the faculty in 1969. He's been there ever since. One of the people Raj worked with early on at CMU, Ralph Guggenheim, now works with George Lucas. The rest of Raj's story is history. And he's going to describe to you some of his thinking these days. But I did ask Raj, as I ask all the distinguished lecturers, what is their message to this group in one sentence? Well, it turned out to be a little more than a sentence, but it's highly controversial. I'd like to share it with you. The one sentence is, it is the best of times, it is the worst of times. Not original. The best is that we participate in an exciting, dynamic, challenging field. Things happen so fast, we can't keep up. Our heads are spinning. The worst of it is, our heads are spinning and we can't keep up, and all this change is taking place. The 90s will be disastrous for the computer industry worldwide. This implies that the job market for our students will also go down. Our industry is likely to go, the information industry, to go from $300 billion a year to $200 billion a year. And that $100 billion shortfall will reflect itself in a severe lack of jobs. Just what you wanted to hear this afternoon. Indeed, we are undoing ourselves with all this progress. We have 2 options. 1, work like the devil to build new software tools and applications, like another Lotus 123 or something more sophisticated, to take up the slack and increase the marketplace. The days of 30% compound annual growth rate are gone. We already have 10% of the gross national product. At best, we can go to 15 or 20%. You don't continue to grow 30% with those kinds of constraints. So indeed, we have to learn to live in a steady-state world. At best, we are now in a zero-sum game. We win, somebody else loses, and vice versa. When you sell a digital watch, you don't sell an analog watch. Things are replacing other products. Second possibility, form a cartel, as the Japanese have done. You gotta believe there's a cartel out there when it costs you $7 to buy a cup of coffee. And there's something at work there maintaining that price and those profit margins. This is one way to keep the profit margins up. Of course, it's totally counter to a free market economy. This is a game of survival. Survival of the fittest implies the next 10 to 20 years will be chaos, and those who emerge at the end of that period may or may not be Americans. With that positive note, let's welcome Raj to tell us why and who needs a supercomputer on a desktop.
Thank you, Len, for that exciting introduction. And actually, it might have come through more bleakly than I thought it sounded when I was listening to Len. But there are problems, and I've been kind of concerned about it for a number of years. And this talk is an attempt for myself to work myself through what are the kinds of things we might do with the kinds of computational power we see coming down the pike. And my talk will consist of 3 parts. First, a set of things I believe we'll all be able to do, every man, woman, and child in the world, that increases the market to 5 billion people, and 5 billion units is a lot of units to sell, if we can get there, even at $100 a piece. The second part is a comic relief, which is called a small script called Flash Forward, to keep you entertained for a little while. And the third part will be to tell you a little bit about the research in robotics and other things we're doing, all of which require, without any doubt, billions of operations per second computation. And then we'll conclude with the talk. So if we can turn down some of the lights and then turn on the projector, the slide projector, and we turn it down to a level where you can all see the slides. The next three slides here are taken from DataQuest, which was trying to project how workstation power would be in the next 4 or 5 years. And this goes from 1989 to 1993. We're already past 1991, so you can validate for yourself whether these numbers are right or wrong. There are 3 columns, red, green, and blue. Red is the entry-level workstations. Green is the traditional workstations, and blue is the high-end workstations. So in 1989, we saw workstations with 16 megabytes of memory. These days, at least at CMU, we don't buy anything less than 32 and often 64. Several of the workstations that in my group we use 128, we're still running out of memory for these complex algorithms. And in 1993, the entry-level workstation, we believe, will be a minimum of 64 megabytes. Next slide, please. The next slide is the power, computational power of these workstations. I'm only going to look at the entry level. You can kind of quickly look at the others too, faster than I can speak. We started with about 12 MIPS in 1989, and we believe it will go to 20 and 50 for the entry level. This is the basic system that every student might have at UCLA. The next slide, please. And the cost, on the other hand, will go exponentially down the other way. And we're estimating the $15,000 workstation in '89 will cost less than $6,000. In case you're thinking these numbers are aggressive, you might have seen an ad in the papers by HP last week where they're announcing for $5,000 a 36 MIPS workstation that you can buy today for $5,000 list price. That means you'll be able to get it for $3,000. Next slide, please. So what all of this says is we've been living in this exponential world, and the rate of exponential change, instead of slowing down, is actually increasing. And this has been the case in the last 3-4 years. And it's been a source of major interest and somewhat concern for me. And it used to be you would double in performance every 2 years. That meant this is exponential growth. In 20 years, you would get a 1,000-fold improvement. Now, in the last 4 or 5 years, that rate of change has increased from 24 months. We are doubling every 15 months. And that means we will get a 1,000-fold improvement every 12 years or 13 years. And I've been asking my friends in industry and others that would know, is there any likelihood it will slow down, and where and when? And nobody can see the end of the tunnel yet. And they're expecting this exponential growth will go on for the next 10 years for sure, but maybe for the next 30, 40 years. And if we continue at the exponential rates for the next 30 years, you can all do this calculation, we will have 100 quadrillion operations per second workstations. 100 quadrillion. Not trillion, not tera-op machines that are in the vogue today. Not 1,000 tera-op machines, but 10 to the 17. Not 10 to the 12, not 10 to the 15, but 10 to the 17. It's a mind-boggling number. And one of my colleagues, Hans Moravec, who likes to engage in mind-boggling exercises like science fiction, wrote a book in Harvard Press that has been published by Harvard Press called Mind Children, where he predicts by about that time, around another 50 years, the number of transistors in computers will exceed the number of neurons in all of our brains by 2 to 3 orders of magnitude. At that point, even if the transistor is only 1/100th or 1,000th of the power of a neuron, you will be able to do the kinds of operations that a human brain can do, except the human brain operates at a 5 millisecond cycle time. And this will be operating at 5, not picoseconds, but 5, a few hundredth of a nanosecond cycle. It's again 6 to 7 orders of magnitude faster. So what he says is, when you're talking to these computers, the computers will talk between each other at high speeds and high intelligence or whatever. When you talk to them, they will think you're a little baby talking to an adult, babbling once in a while. But by the time you finished your first word, they've already figured out what you're going to say for the next 3 minutes. So that's the world we're likely to live in, and it's kind of both fascinating and controversial and scary. But forgetting about the 50-year future, and many of you will be alive, and I hope I'll be too, with the miracles of modern medicine. I'm also expecting to be alive in the year 2150. Or 2750, whatever. We can all hope. But clearly, even in the near term, next 10 years, we can predict things are looking very dramatic. Next slide, please. This is not only the case with computational power, it's also the case with communication speeds. Essentially, our friends in Bell Labs and other places tell us the transmission capacity and the bandwidth will be unlimited, essentially, with fiber optics. And you have your own local guru and expert here in Len, who has been, in fact, studying and actually helping us to make national policy in this area on gigabit networks and beyond. In addition to that, wireless communication and low-cost communication, even 64 kilobit ISDN, which everybody can have for under $30 per month, essentially the cost of the telephone service. Think of it for a minute. A 500-page book can be transmitted from anywhere in the world to any other place in the world in less than 40 seconds with an ISDN line. Why? An average book of 500 pages has about 1 million characters. With some simple linguistic coding, you can get it down to around 300,000, 400,000 characters. This is 8,000 characters per second. Multiply it out and you'll get, and for less than the price of a cup of coffee, anybody, anywhere in the world can access any book in the Library of Congress. Not quite, because if they have images, if they have drawings, and if they have other things, it may be more, maybe 3 minutes instead of 30 seconds. But that is the range we're talking about. So even at the lowest possible bandwidth rate we're talking about, the kinds of things we'll be able to do will be phenomenal. With the gigabit networks around the world and other types of communication, it is not even possible for many of us to think of the possible consequences of this. Next slide, please. So my purpose here is to kind of talk about the kinds of applications every person would benefit from over the next 10, 20, 30 years in the first part of my talk. And the first set of things we'll be able to do with is making computers easier to use, what I call silky interfaces. Interfaces that use speech, image, language, and knowledge so that they are able to make us make it possible for us to use computers easier than ever before. You can speak to computers. What happens when you speak to computers? You get a bunch of numbers digitized, and you get anywhere from 8,000 bytes to 32,000 bytes every second. And you multiply that out, an hour of telephone quality speech is about 30 megabytes, 28 megabytes. So, and if you want stereophonic CD quality, it's about 635 megabytes. 30 years ago, when I started working on speech, 28 megabytes was too much memory. I couldn't store it anywhere. Okay. If I had a megabyte of memory on a computer, that was already a big mainframe. These days, every workstation will have 28 megabytes. So you can have online in the primary memory multiple hours of speech. Why? Because there are quality preserving compression techniques, which we now already have, which will compress the speech by a factor of 5 without any loss of quality, maybe even a factor of 10. I've heard some speech at Bell Labs at 8 kilobits per second. Very high quality telephone speech. And at that point, we're talking about 3 megabytes per hour of speech. What this makes it possible now, all of a sudden, I don't know why you might want to do it, but let me take you through. If any of you were so interested, you could capture everything you've ever spoken in your entire life, from the time you were a little baby, baby babble, all the way through the time you die, in less than 100 CD-ROM disks, 100 gigabytes. Everything that you've ever spoken. This would be a voice-activated thing, and we did the calculations, and what that gives you, essentially, at 100 gigabytes, is 300,000 hours of speech. And if you speak for an hour a day, and you'll have a lot more capacity left over. If you speak for 3 hours a day, you'll barely make it. Now, what can you do if you can speak to the computers? Next 3 slides will show us some of the simple examples. You can do things like voicemail, voice annotations, and time compression. Next slide, please. The simplest thing you can do, and I do this routinely now using a Next workstation. I'm sure all of you can do that too, because all the workstation manufacturers are coming up with multimedia, and so it's not just Next. So here, this is an object-oriented mail system, so you can essentially record a voice message and ship it. Every time there's a voice message, a lip symbol or some icon will appear, and if you click on it, you can get the message. Right? And in this case, this message was from one of the people working with me. He says, I've got a program. If you want to operate that program, you listen to the operating instructions, and then click on the program icon, and you can run it. And the idea, you could ship me a program, and by just clicking on that thing in my mail, I could run it, was already mind-boggling to me, because that's something we couldn't do even a year ago. But if you had 1 billion operations per second computer, you're not, right now, the only way I can run that program is to be binary compatible. Your workstation, my workstation, should use the same binary images. Then the object that comes across will execute automatically. But if I have 1 billion operations per second system, a 3G PC, then the minute I click on it, it will immediately compile and execute, or even if it has to be interpreted, it's not a big problem. I can run it instantaneously, because the kinds of power we're talking about is 100 times more than what I have here. Next slide. So you can obviously send voice messages back and forth, and that's already a useful thing. The second very important thing for teamwork or collaboration or collaborators is being able to communicate with each other by being able to attach annotations on documents that you're working together. So we all write papers together, and I read your paper right now. If I wanted to send you comments on your electronic mail, it's a very painful process. I have to copy your stuff and then put something in, put some carrots or something, and then put my comments underneath, and back and forth. It's very painful. In this kind of a multimedia environment, all you do is point at the word or the phrase or the sentence that the other person has written and say, I disagree with this phrasing, I think you should do X, Y, Z. And as you speak it, that'll be captured as a sound object, and then you can mail it, whole thing back, his document with your annotation with no problem at all. Very simple, doesn't involve a lot of complicated things, except you need an object-oriented operating system and an object-oriented mail system. Next slide, please. The next thing is very interesting. It didn't occur to me until I was preparing this talk. We now have enough technology for processing a speech signal to remove not only the pauses and the ums and ahs and other kinds of things, plus look in the middle of the vowels, and if you, especially if you're from Texas or something and drawing in long vowels, clip off the middle third and still have no loss of intelligibility at all. And I've tried various experiments. You can get compression rates of anywhere from 20% to 50% with these techniques. And what that says is, in the future, you'll be able to listen to my talk, which is now wasting 1 hour sitting here and listening. I can ship you my whole talk as an electronic mail message, and you'll be able to listen to it in half an hour. So think of the productivity of that. Furthermore, if you find that this part you already know, you can do fast forward, which you can't do now, right? Next slide. So in addition to the simple uses of using speech, this is for every person, this is. There are also other things that would be very useful, as you can begin to recognize the speech that is spoken. And that technology is there, and I'll show you some examples of it. So you can use it for entry of data, and you can use it for database retrieval, and then we and most interesting one is this ability to transcribe dictation or voice messages. One of the things I found as I was using this voice message thing is some people tend to be very verbal. They can't get to the point. They keep talking and talking and talking, and I have to sit there listening and listening and listening. After 10 minutes, I finally get to the point. Unfortunately, if it is a typed message, I can scan. And anytime I get a message longer than one paragraph, I can see on the thing, it scrolls up at the full speed of scrolling rates. Whatever I can pick up is all I read. So if you're sending me a message, please send one paragraph messages. Anything more will not get read other than at scrolling speeds. And so on. So what do I, so obviously if you have a voice mail system, it would also be nice to have a transcription of it. And we have a technology, next slide please. And currently, this is, next slide please. We'll skip this one. This is the actual, one of the people read the original message on the left-hand side, and the programs that we now have try to transcribe it. This is an unlimited vocabulary speech recognition. Currently, the systems are not that good. They make an error every third word, so to speak. And we have done some protocols, and if you look at the second paragraph, where only 2 or 3 words are wrong, you can almost read and figure out what the person is saying without too much difficulty. In the first paragraph, where almost every third word is wrong, all the white spaces are wrong in the left side. Then, that part, that's not very readable. We believe by the time we have this 3G PCs in 1995, we will have systems that are working with the accuracy of the second paragraph, but there will be an error 1 out of every 20 words or so, or better. At that point, it's almost readable and good enough for indexing purposes, storing and retrieval and so on. And in the past, we used to think the transcription has to be perfect because we were always thinking we're going to throw away the speech. Not so. If I can store everything I've spoken from the time I was a little baby to the time I die, I can certainly store any messages that I might send, you might send. An interesting statistic, John McCarthy, who is one of the people who has faithfully kept all the messages he's ever received, not like me, says all the messages he has ever received from 1968 till now only take 84 megabytes. That's it, 84 megabytes. So it just shows that we're not talking about very large amounts of disk space. The only thing, of course, is now with all this broadcasting and people spend sending long messages, perhaps there will be a lot of garbage which needs to be rid of. So, with this kind of a transcription, which is almost around the corner from my point of view, that's 2, 3, 4 years horizon. Now, every time I get a voice message, I keep it. It's a semi-permanent, it's a permanent record. And now the fact that there are occasional errors no longer makes any difference because I can point at some part and say, I don't understand what this is, play me the original message. I can hear it. So now I have a random access into an analog tape, if you will, which was not practical before. With this transcription, I have back pointers from every word and every phrase back into the original signal. Okay. So it gives me a capability that didn't exist. Next slide, please. Now we'll skip to the second part of my silky interfaces, the image processing. Images, in general, generate 100 to 1,000 times more data than speech. And again, this is something that is well within the means of today's computers. Every time you take a page and scan it and send it as a fax, you're doing image processing. At 300 dots per inch, if you scan a page, you're going to get roughly a megabyte. But if you use CCITT Group 3 standard compression, you can reduce that megabyte of memory to 50 kilobytes. If you use Group 4, it's roughly 20 kilobytes. At 20 kilobytes, you can almost afford to keep the entire book as a fax image. Because a 500-page book times 20 kilobytes is about 10 megabytes. Right? Now I can also do OCR. OCR is pretty good these days, 99.9% accuracy. And you can get it on PCs and every kind of systems. Omni font, optical character recognition, any font of any size. Now I have also, in addition to having an image representation, which I'm going to keep forever, I'm also going to scan it and store it and do an optical character recognition so I can use it for indexing purposes, even though occasionally it might be not. So normally, a 500-page book, which would take 500 megabytes if I didn't do any compression, would only take 1 megabyte if I were storing it as an ASCII and assuming there were no graphs and pictures in there. And if I stored it as a compressed fax format, I would use maybe 10 to 30 megabytes, depending on the complexity of the image. And you can also do similar calculations for color photographs, which tend to be a lot more data intensive, 280 megabytes per single color photograph. Or you can look at video of various kinds, including high definition TV and NTSC and so on. And all of these provide you suddenly with the capability of storing and retrieving the entire 2-hour movie in your personal workstation by around the turn of the century. And I'll show you some, when I come to my comic relief, you'll see some real examples. And you'll be able to download the entire movie in less than a minute or two using a gigabit or gigabyte networks, fiber optic network coming into your home. That means you don't have to walk over to the video store anymore. Demand-based video is one of the major potential money makers for computer industry or entertainment industry. Maybe they'll be one and the same in another 20 years. Next slide, please. I'll quickly take you through some simple examples of how you would use it. What would you do with this capability again? The simplest thing we've been able to find, which we routinely are beginning to use, is to use it as electronic file cabinet. I'm trying to take all the file cabinets. I have about, maybe 20, 30 drawers full of stuff. And when you add up all of those, the number of total pages is less than 100,000 pages. Everything I've collected for the last 30 years. And I can scan all of them in and store it on a small number of optical disks. And again, you can do this calculation. You can store about 40,000 pages per gigabyte using compressed fax format, if it's just text or black and white images. If you have grayscale images, it will be somewhat larger. And what else can you do? You'll be able to have your own personal digital libraries of thousands of books, not taking up too much space in your office or at home. What else can you do? Already these digital cameras and digital movie things are already commercially available. You can buy both from Kodak and Canon for a small price of about $2,000 to $3,000. all digital cameras. No more film. It's all digital. You download it. It's a SCSI interface into the computer, and you can store all your photographs in digital form in your computer. And any time you want it, you can print a hard copy, color hard copy. And color hard copies in the printers are are beginning to be routinely available. You probably saw the ad from HP. You can buy a color printer for $999. So if you're not making color overhead projector things already, you should all invest in one of those. If you go to the right dealer, you can get it for $500. Actually, yeah, it turns out. The HP color printer. So all kinds of very exciting possibilities with image processing. None of these yet come to the point of understanding what is in the image. Next slide, please. If you can also understand what is in the image and do optical character recognition, content-based indexing, a large number of other things become possible, which we'll come to towards the end of my talk. Computers that can read and understand books, right? And answers questions at the end of the chapter. So here is, again, our annotations in the margin. Imagine if you could have captured all the scientists going back to Einstein or before, as they were writing their famous papers, if they could have also left verbal commentary on the margins for you, so that future generations could not only read their papers, but also could have the benefit of listening to them speak and see why they thought of what they're saying. But no longer. All of you Einsteins in this room will be able to leave for the posterity for the rest of the eons to come all your great ideas, so that the rest of the world will be able to hear it. And it will be stored forever. Next slide, please. So the third part of my Silky interface is use of language as part of the user interface in human-computer interaction. There are a number of things that are already practical and are routinely available, such as reading aids and writing aids, and translation aids, and intelligent indexing and filing assistance. And my favorite one here is proposal writing templates. Basically, I want to go to my computer and say, generate a new proposal for speech recognition. Use all the past stuff and papers I've written and so on. And then it produces all this boilerplate and everything else, and I spend an hour to add a few things. And then the computer sends it off electronically. At the other end, at DARPA or NSF, none of the computer reads all of this. Not the program manager. And then gives it a score, and the program manager then decides whether it's going to fund it. But without even waiting for that, there are a number of style and grammar correction systems already commercially becoming available. Those of you who are non-native speakers like me would strongly benefit by using such things. Then next slide, please. Translation assistant. One of the very interesting uses we found, especially if you're in a global economy and you've got to write letters and other things back and forth. Here is an example. I have a document that comes in, a letter, let us say, comes in from Italy. I scan it in, do an OCR, optical character recognition. So I have all the words. And let us say I don't know anything about Italian. So I might have to take a 1-hour lesson in Italian so that I know a few hundred words, at least for the first time, a little bit of the grammar, a little bit. Even if I don't know it, I can learn it by osmosis. And so I start reading. And I don't understand the first word. I say, what is that word? Instantaneously, within less than 100 milliseconds, in a window will appear the meaning. Not 100 different meanings. If you take a dictionary and open it, on the average, there are 17 possible entries, 17 possible different meanings for every word in the dictionary. However, in a given context, only 2 or 3 are appropriate. So instead of having to read through all of that and spend 10 minutes before you figure out which meaning is useful, here, by doing simple contextual analysis, not very sophisticated language processing, simple contextual analysis, you can reduce the number of meanings from 17 to 2 or 3. And that appears within 100 milliseconds, so that means you have some hope of reading a foreign document without having to go to a translation service and paying through the nose, and even then waiting 3 days before you can read it. So suddenly we are beginning to have the capability where people can communicate with each other around the world without feeling what you're trying to communicate may be misinterpreted or misread or not understood at all, or thrown into the wastebasket, which is what happens now when you get a letter from Russia or some other place. So we're also working on translation, machine language translation. The technology is not here, and we believe will not be here for at least 30 more years or more to do full-blown metaphorical translation of metaphorical language. Manuals, computer manuals will be easier and will be done sooner. But things like novels and metaphor and other types of things are going to be extremely difficult, and we don't yet understand how to translate. But we know how to translate phrases without worrying about the whole sentences. So phrase-based translation will be appearing in another window, and it's a word by word, so you'll be able to read, use in a human-computer symbiosis together, working together, you'll be able to read the document with no problem at all. So there are a number of potential uses of language, which for lack of time I won't go into. Next slide, please. So the last one of the silky interfaces is the use of, can I get a glass of water? Is the use of knowledge in the interfaces. As I was telling Len, my favorite example is I get very tired reading manuals of this thick, this high. And every time you order a PC or anything, you're getting manuals, they're stacked in my office at that time for PC or all the applications. I don't have enough lifetime to read and master all of those things. I only use them once every 8 months or once every 6 months. I forget by the time I come back. So what I need is a system that will look over my shoulder and help me, especially if I'm doing something silly, and to come back and say, did you know you could have done this better with one command instead of typing 5? And those types of simple intelligent assistants are possible today, but it requires joint work by universities and industry so that all manuals are online and all knowledge in the manuals is captured in various ways so that there's some kind of a self-awareness on the part of the computer or on part of the application so that it can in fact explain to you what it is that you're trying to do that's wrong and how you might be able to do it better. Broadly, that's a special case of a monitoring of a process. Broadly, every kind of monitoring by computer, leave alone problem solving or doing more very sophisticated, simply monitoring things and then helping you to save time and money is the thing that's going to be the biggest seller or the biggest source of increase in the market size for computational engines. And in particular, if we can get to a stage where a home computer not only gets you information, but by monitoring your bank accounts and your energy consumption and your telephone charges and everything, would save you a few $100s a year. That would more than pay for the computer. The return on investment on a $3,000 supercomputer in year 2000. And this leads to the two killer applications I believe will be ubiquitous. One of them is essentially access to knowledge and information. Large, very large knowledge bases and very large databases, including the Digital Library of Congress and Digital Library of all the movies that you can download, will be one of those applications. And a special case of that is essentially an electronic shopping service. You might have read the news items recently about interactive TV. They're already going to be here in the next 2, 3, 4 years. But broadly, a computer TV. Incidentally, we have a project starting now on operating systems for a computer TV. And this is a DARPA project. We believe every TV will have an operating system inside of it. And it will be a multi-process operating system. It will be monitoring 60 channels. And it will be able to give you instantaneous replay for the last 5 minutes on any one of those channels. And it will do all kinds of other interesting things that we can't do. But the common, most important thing that will save money and thereby cause people to buy it, and thereby, just like a car, you would only buy a car if at least you get in the car and drive it once a day. If you don't touch your computer at least once a day, you won't buy it. So you have to find applications, killer applications, that have that property. So electronic shopping, we believe, is going to be such a thing. And we don't have the infrastructure. Len and Bob Kahn and others have worked on the whole national network application, and we need that. We also need databases and services and other things from retailers and other people that attach to those things to begin to build that new infrastructure that will increase the size of the market. The second killer application I see is the whole area of collaboration. Collaborative writing, collaborative design, collaborative planning. Anywhere a group of people have to work together to solve a problem or something. Now that group can be both distributed in time and space. You don't all have to get into one room, fly from all over the world and meet in one room to do the thing that you need to do. You'll now be able to be anywhere you want. And there's a very special implication of that for education. One of the biggest problems we have today is everybody that wants to listen to this lecture have to come into this room and sit and listen to this lecture. There are people in the world, the best teachers in the world. It would be nice to be able to listen to, again, distributed in time and space. And I believe with these multimedia workstations that are coming online, we will be able to have that benefit. So you no longer all have to sit in the same place at the same time to have the benefit of the same lecture. In addition to the video mail, we'll talk about the voicemail. The most common, predominant thing will be video mail. So you'll still be interacting with your professor. You can say, Professor Kleinrock, I don't understand what this is. And that context, and with your video mail question, you'll go to Professor Kleinrock, and he will be swamped with all these messages. But you will have an intelligent assistant which says, I've already answered all these questions. Go look at the bulletin board of my video responses. And 99% of them already been answered from last year. And if you come up with a new question that I haven't answered, you get a special prize. So those are the kinds of applications we've been thinking about. What I would now like to do is show you this comic relief I do promising. You can turn off the slide. Can we turn off the lights, please?
Morning. Hey, yeah.
Good morning, Kate. It's April 1st, 1997, and the time is 6:30 a.m. Kate News Selection reports new trade agreements between Japan and France affect Paris spring collection, plus 24 other items of interest. Care to Brown?
Not now. Hello.
Mail served here. 43 items, including 26 unopened for 3 days, 12 unopened for 2 days, and
Cancel list. Oh. All right. I can use it.
canceling. Were there further instructions?
Yes. Did my snap catalog arrive?
I understood catalog. Snap. Check.
Oh, right.
Enthusiasm detected. from staff headquarters, priority 1. You wish to preview Mr. Smith.
Darn.
You've used that before. You care to decline it?
No, phone call, preview call. Hello, I smell trouble. Ugh. Okay, VidPhone, open connection.
Hey, are you there? I haven't seen you.
Sorry, George, not exactly dressed for success this morning.
Seen the customer version of our spring catalog yet?
Yeah, I just got it in the mail. You guys don't exactly waste time.
You did one heck of a job, Kate. One heck of a job. I love that history of the t-shirt segment. Wonderful. Sales are...
It cuts the chase, George. You didn't stay up all night to call and compliment.
Kate, you are the best interactive designer. I mean that from the bottom of my heart. But I got a little emergency here. You know that blue jeans spectacular that you're working on?
Did you know that blue jeans were invented during the gold rush? A major moment in American culture.
I know that your due date was next week, but gotta move it up.
Don't do this, George.
I need it by today, 5 p.m. We're going into production tonight.
Tonight?
Orders from the top. And our competition is breaking early. They're doing the jeans retrospective too. We got to be better. We got to be first. The future of Snap depends on you. Oh, and there's something else.
You're changing the concept on me, George.
You gotta take the history of our blue jean story into the future. End your segment with a forecast of the jeans of the future.
And no one can predict fashion, George.
If anybody can, you can. Okay. Yeah.
VidPhone, get Sam Galloway. Try every number. Copyright status?
James D. image unavailable. Copyright Paramount Studios. Last usage granted $15,000 to Levi Strauss for in-house promotion. One time only. Alternate suggestions.
Yeah, let's see. Image search, circa 1959. Blue jeans, male, sex appeal.
Searching Texas. Access other data banks.
Picture perfect, fashion source and alter image.
You have to be reminded. Search on Alter Image Data Bank is very expensive and likely to exceed your monthly online budget. Cost is $4.85 per 1,000 image scan.
Just do it. I'll fight that one later.
Searching. Did not understand last command.
Do it, do it, do it.
Understood. Hey, still unable to reach Sam Gallagher. However, the teleconferencing call request is ready. Have Snap Corporate Los Angeles and Paris office both online. Do you wish to be seen?
Previous.
As originator of the conference call, you wish to choose resolution on live video.
What up?
Default settings confirmed. You ask to be reminded, full video from Paris is expensive at $3.55 per minute. A call of less than a minute will exceed your budget of...
Got it. Top resolution on George. Face only on Timothy.
Understood. Conference call open.
Hello, everybody.
Hi there.
Can you all see each other?
Yes. Oh, hey, you look great, Genevieve.
What did we do before video phones?
We did not dress for phone.
Oh, come on. Nice dress for you.
Oh, listen, guys, I really need your help. As George knows where I'm done, I need something on the future of blue jeans. What's the forecast in Paris?
Paris girls are going to a retro bell-bottom look. I certainly don't like, but
Neither do I. Kate, Paris is behind California in acting. No offense, Genevieve.
Listen, I'm grabbing at straws. What about in Hollywood?
Well, my sources tell me that bows are at the end.
Forget bows, ladies. Market research mixes bows.
Sorry, Genevieve.
Just trying to help.
Look, I'm sure you two are going to come up with something. I gotta go. We're going to have another teleconference call with you.
Satellite feed has become available. You wish to receive Paris in full resolution at only 185 per minute.
Yeah, go for it. Terrific scarf, Genevieve.
Just some old thing. Look, with some photos help, I could send several, only at least 2 are public domain. Really nice jeans.
You're an angel. Send the 2 free and clear ones full res, please, so I can just bump them right in. But what am I going to do about jeans of the future?
Don't listen to George. You need a trip to Paris.
Right. By 5 today. Jeans of the future. I need an idea.
Understood that you need an idea. Please give context for data search.
No, just let me think. Media maker file, review jeans retrospective.
140 years ago, the first jeans were made in California out of the same canvas used for tents and covered wagons. The canvas was quickly replaced by a tough cotton fabric called denim in a deep indigo blue color, beginning a tradition of real jeans designed for real
We do it your way. Of course. An interactive jeans catalog, that's it. Pick and choose your options. The jeans of the future, uniquely yours.
Incoming priority 1-bit phone call. Sam Gallagher returning. You wish to preview Mr. Gallagher.
No. Big phone connect.
Katie, you can try to reach me.
For hours. I need your help. Are you anywhere near a college campus?
I might be. What are you looking for?
Can you get me 8 attractive talking heads in the next 45 minutes?
Don't I even get it alone?
I've got to close out a blue jeans retrospective in the next 45 minutes.
This is going to cost you, Kate.
I knew that when I called you, Sam. Listen, here's my idea. Jeans of the future will be custom styled. Instead of just stone-washed or regular denim, 5 pockets or 4, you'll be able to order your jeans like me. Exactly the way we like them.
What about fit?
Well, I'm going to be custom too. Yeah, let's see. You can get measured at any snap outlet, and the template can be made to your body shape. Perfect. One-of-a-kind blue jeans. What could be more American? But I need some visuals.
Got it. Gorgeous college kids, talking heads. I'll ask them, what do you want in the jeans?
That's it. I've got 3 graphic artists standing by to do sketches of their answers. Can you do it? Are you near a college? Can you send a live feed?
Consider it done.
I like faded blue jeans that sort of conform to your body.
I like 60s bell bottoms. A narrow at the bottom and thick one.
I don't want blue.
I like the original Levi's.
I like the so much from the 80s.
I like butterfly.
We got the lights on.
Butterfly as opposed to zipper.
I like my blue jeans tight. Medium, faded, not faded, not old.
I like the butterfly.
This goes on for a few more minutes. I don't want to take you back.
take you past your time of this thing. This was not made by Carnegie Mellon. We can't afford that kind of. This was made in Silicon Valley by a group of people, including LSI Logic, who are making these special chips, image compression chips and multimedia chips and so on, and they don't know who they're going to sell it to. And so they made this. So to convince people, computer makers especially, that they should start putting in their chips in every one of their computers, especially notebook computers. And the reason I showed it to you is not only for the comic relief, but just looking at it, you can see the technologies we have to develop. You saw, connected speech and all the ambiguity of language and how you have to interact and what are the problems with that. You saw that issue of how much it costs is no joke. One weekend, I was playing with one of the databases, or multiple databases, using, I believe, either CompuServe or one of the things. I ended up spending $4,700. I didn't know I was spending $4,700. My entire year's budget was blown at that one weekend. And somehow we need to have ways of actually accessing databases, knowing what's costing, like a meter has to be clicking right on the screen. So you know when you're spending money that you don't have, So there are a number of very interesting technological issues that come up within that. I don't have the time today to go into them, but all of them are both solvable, and they're also very interesting, challenging research problems that will be solved in the next 5 to 10 years. And there's a whole set of other things I would talk about another time, but on robotics, because basically, let me take 1 minute to give you 3 examples of things we're doing in robotics. We have a car that drives itself, right? And there are 40,000 people that die every year in this country when they're drunk or not paying attention or fall asleep at the car while they're driving and so on. We believe having an intelligent cruise control in every car, accident avoiding cruise control, over 80% of these deaths can be avoided. Unfortunately, the same technology can also be used by the Department of Defense to build intelligent tanks to overrun Baghdad. You tell me whether we should do this research or not, because it obviously has a major social implication, both positive and negative. Every research we do has the same situation. It's the dual-use technologies. Anything we do for social improvement will also be able to be used for destructive purposes. And one has to kind of say, what do we do? And our take on it is we must do the research and let the social systems define what is right or wrong, rather than us. We are part of the social system. We should be able to help make those decisions also. But if we don't do it, saying DoD is going to use it, then we run the risk of also not doing all the good things that the technology can do. With that, I'd like to thank you all, and